So let me get rid of this little box that's in the way of the last one. There we go. I also think, hold on one second. Let's try to, no, what's it? There we go. Now we can actually read the problem that we're trying to do. Let me share this one last time just in case. All right, so graph of f of x is given below, and we want to estimate the integral from 0 to 6 of f of x dx. So remember, the main thing that we pick up from 5.2 is essentially just this new notation for the integral. In terms of your homework on Wiley, there's not a lot of stuff you'll use your calculator for. We learned how to do it in your calculator, but a lot of the 5.2 homework in Wiley is actually still using the Riemann sums, but it'll just have the integral notation instead of something else. So it might say estimate the integral from 0 to 6 of this function using 3 rectangles or something like that. And so you'll do the same process from 5.1. It's just with the new notation. But anyway, so we've got this. We don't actually have the actual function equation. We're just given the graph. So here we technically could do a Riemann sum. We could do a left hand and a right hand, and we could try to approximate what those y values are by just looking at the graph. But I also want to present a slightly different way that you can't always do, but we can do in this case, because notice that we kind of had to have a grid structure in the back. So when your picture kind of has the grid structure in the back, we have this kind of other option, finding the area underneath of this function. Because remember, that's technically what we're doing here. We're finding areas underneath of functions. You're welcome. And now I've lost my page. I went to a different page. There we go. So we want to find the area underneath of here. And since we kind of have this grid structure here, we can kind of think about it as counting boxes. Like if we just count the number of boxes that show up underneath of that function. So the way I like to do is I like to start with the full boxes. So I'm going to go ahead and just start counting these. So I have 1 box, 2 box, 3 box. That's another full box, 5, 6, 7. That's pretty much all of my full boxes. And now I have to start trying to like piece them together. Now, since this is an estimate, it's not going to be perfect, of course, just like the Riemann sums aren't perfect. But we're going to try to piece the last ones together. So if we kind of look at these two pieces right here, the one at the very top and the one right next to the one I labeled 7, both of those for the area that's underneath of the function are approximately half a box. I know they're both a little bit more than one half of a box, but let's just say for our sanity that they both seem to be approximately half a box. So with them together, we would have an 1/8 full box, if that makes any sense, hopefully. So I'm going to combine those two together to essentially make an 1/8 box. Again, I know it would make a little bit more than an 1/8 box, but we're estimating here, so that's okay. If I take these two pieces right here, and I kind of imagine flipping over that bottom piece onto the top of the other one, that would essentially make another full box, approximately. So we have kind of a 1/9 full box between those two. And then with these last two, since this one here, that one there, it's full in and of itself. If we combine these two together, that's almost going to be like 1.5 boxes as opposed to like 1 box. So let's go ahead and say we probably have about 10.5 boxes underneath of that function. So essentially what I did, since we had the grid structure, I went ahead and counted how many boxes, is what I like to call them, how many boxes we approximately have underneath of that function. So it looks like there's about 10.5 boxes. Now, that's not our answer necessarily. Sometimes it does turn out to be your answer, but it's not necessarily your answer because remember, we want to look at the area. And so we actually need to consider the area of each one of those boxes. So area of boxes. So these boxes are essentially a 1 by 5 box. So 1 times 5 is of course 5. So each one of those boxes essentially actually counts for 5 units. Yeah. So let me erase the 8, 9, and 10.5. So essentially, once I'm done counting my full boxes, I have like pieces of boxes left. So I want to try to start like piecing them together into, more boxes. So if I think about this piece and this piece, there we go. So those two pieces up top that we haven't counted yet, those are both approximately half a box. So if I put them together, they make approximately one box. So between these two, that's going to get me my 8th box. I know it's a little bit more because they're both a little bit more than half a box, but we're approximating, so we can say it's close enough to about one box. And then if I take these two pieces here, let me actually do this. Take this piece, which is almost one full box, but then I add on this kind of piece down here. If I were to kind of flip it up top, imagine. Between those two, I essentially get another box, approximately. So that gave me my 9th box, is kind of those two combined together. And then the last thing I have is this piece here and this piece here. Well, neither of those is one full box, and they're both more than half a box. And, well, the second piece is almost close to half a box. But essentially, if we were to group those two boxes together, the ones I just shaded in red, that's not quite one box. It's probably more like 1.5 boxes. So between the two of those, we would get up to a 10.5 boxes. Does that make sense? So it's kind of like we count up all the full boxes and then we take all the pieces that we're left with and just try to piece them together into more boxes. The best you can. Okay, so we've got 10.5 boxes. Each box technically counts for 5 units. So then if we wanted to actually estimate this integral, it's essentially the amount of boxes you just counted times the area of each box, which is 52.5. So we could say that that integral is most likely approximately around 52.5. Now, again, technically we could have done a Riemann sum here. The Riemann sums probably would have been a bit farther off because we were getting pretty decently close to the amount of area here. We're not doing a lot of overestimation or a lot of underestimation. But again, you kind of have to have this grid structure already there. Don't draw your own grids. If there's no grid, just go ahead and do a regular Riemann sum. But if there's a grid, you can count. But also be careful, because if the instructions tell you to use a Riemann sum, then you need to use a Riemann sum. But if it doesn't specify and it just says estimate the area or estimate this integral, then if you can count boxes, you can go ahead and count boxes. Just remember that you need to take into consideration the area of each box. Questions, concerns on that one? That's the last one in 5.2 we have to go over. So any questions on that before we move on? Wait like 5 more seconds. Okay. All right. So, as I mentioned already, we are jumping over to chapter 6, and we are not doing 6.1. I have never taught 6.1 in my entire time I've been teaching this class. Hopefully changing over to the other. Oh, Kayla, hold on. Let me go back. Questions. So Kayla, I found that there was 10.5 boxes. Now, if the boxes only equate to 1 unit, then I'm good to go. It's just 10.5. But notice that each one of those boxes is technically a 1 by 5 because the X values increased by 1. Okay, my one screen hasn't shared yet. Maybe I should. There we go. So the X values increased by 1, but the Y values increased by 5. So each one of those boxes is technically a 1 by 5 box. So I have an area of 5. So if I want the area underneath of that function, which is what that integral is asking me for, this is asking me for area underneath of the function. Well, if I just found that there were 10.5 boxes, but each box has an area of 5, I need to multiply the amount of boxes by the amount of area in each box, which gives me the 10.5 times 5. The amount of boxes times the area of each box, which when I do that, will then give me that total area underneath of that function. Because it's not just 10.5, because the boxes aren't just 1 unit. Does that make sense? Was it still lagging? It's all up for me. Does that make sense? So we don't just need to take into consideration the amount of boxes, but the area. So we have to multiply the two numbers together to get the total area. Okay. So, any more questions before we go to chapter 6? It's still black for you? How about now? Cool. So I'm going to leave this up for a couple more so you can look at that really quick. Because then we're moving on to a different sheet and hopefully that sheet will pop up. But I'll leave this up for a couple more seconds. I'll kind of start babbling about what we're going to do next. So what we're going to do next in chapter 6 is, so we just found this notation for integrals. And it's telling us the area underneath of a function. And at this point in time, we learned how to punch them into our calculator the other day. We also need to figure out how to do them by hand and not using Riemann sums. So just like with derivatives, how we had the estimation technique of the instantaneous rate of change, and then we actually figured out how to do the derivatives. We're essentially now going to go into kind of the derivative equivalent for integrals. So we're going to be learning how to do that by hand. And some of the things that we'll be doing, some of the integrals we're calculating, you can't actually put in your calculator, and I'll explain why. But that's essentially what we're going to next, is do integrals by hand, but not Riemann sum by hand. Okay, I'm going to switch over now. Boink, boink, boink. Okay. Can anyone not see that? Section 6.2 to 6.3. 5, 4, 3, 2, 1. Okay. All right, section 6.2 and 6.3. So the fundamental theorem of calculus, so it's called the fundamental theorem, so it's probably important, says if capital F prime of x, and I do mean capital, it's a notation thing, and I'll explain in a second. So capital F prime of x is continuous on an interval, goodness, then the integral, oh, that's too thick. Then the integral from a to b of f prime of x dx is equal to regular f of b minus regular f, regular capital F of a. So that is the definite integral of a derivative of a function gives the total change in the function. And we'll come back to that idea of total change in a little bit. And by a little bit, I mean a couple of days. But we'll come back to that idea. But first, we're going to kind of figure out how to calculate these. So if we kind of look at that theorem that I just wrote down, notice that the integral on the left has f prime, and the things on the right are just regular old f's. There's no primes anymore. So essentially, if I can find an equation such that its derivative is the integrand, then I can calculate these by hand. So essentially, we kind of want to go backwards. So now if I wasn't teaching to a screen, I would actually ask you this. I'll probably ask you to think about it for 5 seconds, but you don't have to try to type an answer or anything like that. Can you think of a function whose derivative is 2x? So I want you to think about that for 5 minutes. You don't have to answer if you don't want to. But can you think of a function whose derivative is 2x? So maybe you thought of x squared. Maybe. Yes, I mean, exactly, x squared. So x squared, if you take its derivative, is 2x. So that's kind of what I was looking for here. Is what's the function whose derivative is 2x? Now again, think for 5 seconds, and again, you don't actually have to answer. But 5 seconds, can you think of another one? Doing this to a screen is obnoxious. So if I try to think of another one, What if we said x squared plus 1? If you take the derivative of that, you get 2x. What if I said x squared minus 576? Derivative of that is x squared. And essentially, I could tack on absolutely any constant at the back of that, and the derivative would still be 2x. Was I saying x squared before? The derivative would be 2x. So essentially, I can find, if I want a function whose derivative is 2x, it can be x squared plus absolutely anything. So essentially what we're going to be needing to do with these, because essentially we are going to be going backwards like this, we're going to be finding what we call antiderivatives. But anyway, so essentially the function whose derivative is 2x would actually be deemed to be x squared plus c, where c is a constant. And this is going to be called the family of antiderivatives. So of course we've just gotten used to going forward, and now I'm going to ask you to go backwards. So the family of antiderivatives of 2x. So the indefinite integral is the family of antiderivatives of a function. So the indefinite integral looks like this. And then for antiderivatives, we usually use capital letters. It's not the end of the world if you don't use capital letters, but that's usually how we denote the antiderivative of a function. Is there's no like f prime notation instead of using an f prime, because that would be the regular derivative, and we don't want that. To denote the antiderivative, you usually use a capital. So note that that integral doesn't have any bounds on it. It doesn't have an a and a b. And that's exactly what I meant by some of the things you can't calculate in your calculator. So these indefinite integrals, the ones that don't have bounds, you can't do in your calculator. Sorry, not sorry. But the ones with bounds, you can. And specifically, that's because that the ones with the bounds, the a to b of f of x dx is a number. But the indefinite integral, the one without bounds, is a family of functions. Family because we have that plus c at the end, so it can be a bunch of different functions. So that's why your calculator, well, some calculators in life can do it, but you're not supposed to use the calculators that can. That's why your calculator can't do the indefinite integrals, because it's not a number, it's a bunch of functions. So I'll wait a couple seconds before I move on. Okay, so say we wanted to determine which of the following, so maybe there's more than one, maybe there's only one, is or are antiderivatives of 8x cubed. Now, one way you can check to see if something is an antiderivative is to take its derivative. So let's take all of the derivatives of these things. Let's find capital F prime, capital G prime, and capital H prime. Let's take all of their derivatives. So if I take the derivative of 24x squared, I'm going to get 48x. If this 24x squared was an antiderivative of 8x cubed, this derivative I just took should be 8x cubed, and it's not. So that one's not an antiderivative. If I take the derivative, regular derivative of 8x to the fourth, I bring the 4 down, so 32x cubed. If this is going to be an antiderivative, 32x cubed should be equal to 8x cubed, which is, it's not. That time they actually have the right power on the function, but not the correct constant out front. And then if I take the derivative of 2x to the fourth, I get 8x cubed. If that's going to be an antiderivative of 8x cubed, I should get that that's equal to 8x cubed, which it is. So you can always kind of check whether something's an antiderivative of something else by taking the derivative of the opposed antiderivative. I don't have the word derivative floating around a lot, but you can always take a derivative of an antiderivative and check to see if it's what you were starting with. So we were starting with 8x cubed, so we wanted the derivatives of these choices to be 8x cubed, and that was only the last one. Now, I'm going to give you a list of rules in a second, but I want to try to think about these in general first before I actually just tell you the rules that you can use, because I'm mean like that, I guess. So let's consider the following antiderivatives, or let's try to find what the antiderivative would be just by thinking about what we know about derivatives. So I have 3x cubed, 3x squared, and I want to know a function, I want to know a function such that when I take its derivative, I get 3x squared. Well, if we think about finding derivatives, we always have to, and here it would technically be a power rule, right? Because if we end with a power, it must have come from a power. So if you think about the power rule, we always bring the power down and we subtract 1 from the power. So if we're going backwards, we probably, if we ended with an x squared, we must have come from an x cubed, right? That's the only way you can get down to an x squared with a derivative is if you started with an x. And then what about that 3 in the front? Do I need to do anything to it? Is there anything I need to consider there? Well, if I take the derivative of x cubed, I bring that 3 down, which would take care of that 3 in the front. So actually, I'm done finding my antiderivative. Well, I should always have a plus c at the end. But this, since the derivative of that is 3x squared, and it matched what I started with, that would be the correct antiderivative. Again, you usually don't have to put this much thought into it because we have rules to follow, but I want us to think about them first. We're going backwards. Okay. I mean, it is kind of like a puzzle. So, Ami, we're essentially trying to go backwards. I'm trying to ask you for a function such that its derivative is 3x squared. Now, if you think about doing a power rule, if you think way back when to the power rule of derivatives, you bring the power down and you subtract 1 from the power, right? So we want to go backwards. We're essentially starting with this side and we want to go backwards. So if we're going backwards, if the thing we're starting with is n minus 1, we need to add 1 to get back to the thing we started with. So if I'm ending up with an x squared and I want to know the antiderivative, I'm going to need to add 1 to that power because that would be going backwards in the power rule, right? So that gave me my x cubed. Well, now I need to consider what about the 3 in the front? Well, since the power rule tells me to bring the power down and that power did turn out to be a 3, that power would have just been brought down in the power rule. So I don't have to do anything with that 3 because I've already essentially gone backwards with the power rule by just adding 1 to that power. So adding 1 to the power gave me x cubed, and then if I think about the derivative of x cubed, I get 3x squared, so I don't need to do anything if it's, what if it's 3? Hold on for a second, Ami. We're going to get there, but I want to get there slowly. So hold on to your pants. I shouldn't have said that. Just hold your horses a little bit. We'll get there. But for now, it was a 3, so hooray. But I will talk about what about if it's not a 3 in a minute. But I want to do some other stuff. I want to build a couple other things up first. So now we're actually kind of going to touch upon it in this next one a little bit. So here I'm starting with x to the 4th, and I want to find the antiderivative. So I want to find the antiderivative. So if I end up with an x to the 4th, it must have come from an x to the 5th. Because again, I shouldn't have erased that power rule. With the power rule, we have to subtract 1 from the power. So if I'm going backwards, I better add 1 to the power. I better add 1 to the power. Okay. Now notice that I don't have a 5 in the front here. So it doesn't work out as nicely as the first one because I don't have that number there. So let's think about what this derivative would be so far. We would get 5x to the fourth. It's lagging. There we go. 5x to the fourth is what we would have so far. So essentially I have the x to the fourth, but I have this extra 5 in the front that I don't want. So think about what you can do to get rid of that 5. If I want to essentially cancel out that 5, if I had a 1/5 in the front, and then I take the derivative, the 1/5 comes along for the ride, and then when I bring the 5 down in the power, those two cancel each other out. So if I have a 1/5 in the front, it's going to take care of bringing that power down because I didn't have a 5 in the front of my original thing, so I needed to somehow cancel it out. Okay, so that's kind of, and again, we're going to show the official rule in a second, but that's kind of what happens when the number in the front isn't what you want, is you kind of need to think about what you need in the front to cancel out whatever you didn't need. So I'll go into a bit more depth in a second, because what if, you know, it's kind of there, but not really? What if the first one was a 6? So it has a 3 in it, but not, it also has a 2. So we'll touch on that a little bit more in a second, but that's kind of the idea that we're going to build up to, is that we not only 1 to the power, but sometimes we're going to need to consider how to get rid of that constant in the front if we don't need it. Let's slightly shift for a second before we get there. Take a breather. What if I started with 5 and I wanted to go backwards? What function, when I take its derivative, gives me 5? So if you think back to our derivative rules, what derivative rule ended up being just a number? Whoops, sorry. And that would have had to come from a 5x. Oh, I should have put a plus c on the back of that. Always add a plus c. And that'll be in our official rules. So, so plus c on this one. But essentially the thing that gives me a derivative of 5 is a 5x. It gives me the derivative is 5 other than 5x. Done that one. What about if I start with e to the x? What function such that, what's a function such that its derivative is e to the x? Well, since e to the x essentially stayed itself when we take derivatives, it's also essentially going to stay itself when we go backwards. So that's just going to be e to the x, but we always have a plus c. And remember, the plus c is because since we're going backwards, you could have technically always had a constant at the back, and the derivative of a constant is 0. So we kind of needed to consider the fact that there possibly was a constant back there. So that's why we tack on the plus c at the end, because it's possible, since we're going backwards, that there might have been a constant there and we don't know what that constant is. So we're just going to say plus c. So we're essentially taking our derivative rules and going backwards. So one last one before I write down the official rules. What's a function such that its derivative is 1 over x? What derivative rule gave you 1 over x? Yeah, technically I didn't. Oh, Lord. Oh, Lord. Number 4, that shouldn't have been an f prime. That's true. I didn't technically check my answer. That's not necessary with these, but yeah, technically you can check your answer by taking the derivative of the supposed antiderivative. So yeah, let me write those down. Let me write them down correctly, which I didn't do apparently. There we go. So yeah, sorry, you don't need that, but since I was doing it on the first 2, I should be consistent. All right, so what derivative rule gave you 1 over x? Now that came from the natural log of x, right? The derivative of the natural log is 1 over x. Now for a second, you're going to have to trust and believe me, and I'll explain it when I write the official rule. So I do agree natural log of x, but we're actually going to pick up an absolute value around that. Trust and believe me for a few seconds. Plus c, because when we take the derivative of that, we don't really consider the absolute value. I'll explain the absolute value in a second. But the derivative of the natural log of x is 1 over x. So we're essentially going backwards. Trust and believe me on that absolute value for a second. I'm going to explain it in a minute. So just like we had derivative rules, we have antiderivative rules. So let's write them down. So yeah, let's just write them down. And then we'll hopefully have time for a few more examples with the actual rules under our belt. Now I'm going to write these in terms of integral notation. Because I should be clear. So I can ask you to find an antiderivative without phrasing it as an integral. That's perfectly fine and acceptable. I can say find the antiderivative of this function. But if I ask you to take the indefinite integral of a function, that is the exact same thing as asking you to find the antiderivative. Okay, so just saying find the antiderivative and writing it like an integral is the same thing. The integral without bounds is the same thing. Okay, antiderivative, integral without bounds is for our intents and purposes the same thing. So if I have an x to the n, if I have a power, the antiderivative of that is essentially you add 1 to that power and you divide by the new power. And you always tack on a plus c. Now, if you want to write this as a fraction on the outside as 1 over this and then that, that's perfectly fine. Whatever floats your boat. Now, this only holds when n is not equal to -1, because the -1 case is going to be the natural log situation. Whoop. If we have the integral of just a constant, now I have to use k for a constant here because we have our plus c's at the end. So if I want to take the antiderivative of just a constant, that's that constant times x plus c. You'll always have a plus c. Antiderivative of e to the x is e to the x plus e. And the antiderivative of e to the kx is 1 over k e to the kx, which kind of makes sense because if you think about the derivative, we brought the power down, so now we want to essentially cancel out that power that we're bringing down, so we have to divide by it instead of multiplying by it. Just like the derivative one, it was technically a chain rule. This is technically something called a u-sub. Technically a u-sub. So again, I don't really like that your book presents it now, but it does. So there it is. And then the antiderivative of 1 over x, which remember is technically x to the negative first, which is why we don't include the negative first case in the power one. This is going to be the natural log of the absolute value of x. Now let me explain why the absolute value is there. Let me do it in a different color. So here's why the absolute value is there. Think about the natural log of just regular old x. And say I wanted to take, well, let me write this, equals f of x. Then its derivative is 1 over x. What if I have the natural log of negative x as my function instead? Now that's technically a chain rule because negative x is still more complicated than just regular old x. So the derivative of that would be 1 over negative x times -1, the derivative of negative x, which reduces to 1 over x. So essentially we have that both of those derivatives is 1 over x. So if we're going backwards, but it came from, one of 2 possible functions, since it's x versus negative x, that's why there's an absolute value there. If you're curious. Otherwise, just trust and believe me and always put an absolute value around it when you're doing antiderivatives. So hold on for a second in case y'all are still writing that down. We'll write down a few properties of integrals and then we'll be able to do a few examples before we're done today. So we have a few properties of integrals. Now they're very similar to the properties we had of derivatives. I might not have called them properties, but let me try to keep as much of this in here as possible. Let me scroll down past the power one because hopefully everyone has that down. There we go. So if we want to take an integral or an antiderivative of essentially a function plus or minus another function, just like with regular derivatives, you could kind of take the derivative of each piece separately. Same idea here, is we're going to take the integral of f of x and then add it or subtract it to the integral of g of x, depending on which one we started with. Now, don't panic that there's suddenly two dx's. Remember, the dx is just notation that is necessary to, write an integral. And in terms of our class, it doesn't really mean a lot for us. But whenever you write an integral, there has to be an integral symbol and a dx. If you don't have both of them together, you don't have a proper integral. So we're essentially saying, since we want to split this up, we have to have two integral symbols and therefore two dx's. But it's essentially just like it was with derivatives. We take the derivative of each piece separately. Here we can take the antiderivative of each piece separately. And remember, the antiderivative is equivalent to saying the indefinite integral. So I've kind of been using integral and antiderivative interchangeably because I can. And then the other one is if we have an indefinite integral of a constant times, well, maybe I should, well, no, maybe I'll change it to a k because we have the plus c's. But if you want to write a c, that's what I technically have in my notes. So remember, with derivatives, if you had a constant in the front, the constant just came along for the ride. Same deal here. So we say we pull the constant out front, but it's essentially just that the constant kind of comes along and then you take the antiderivative of the other thing. And the constant just kind of chills. So very similar to the things we used for derivatives. So I'll wait another minute in case y'all are still writing that down, and then we'll do a few examples of these using our rules that we now have. And so this is essentially, this piece that we just wrote down is essentially what's going to take care of kind of your question about what if it's not the actual number that we need. We're essentially going to have that constant just kind of stick around, and we're just going to do the generic rule on the last piece, and then we can simplify things at the end. You'll see what I mean in a second. Well, hopefully you'll see what I mean in a second. All right, so let me try to leave those in there a little bit. So let's say we want to find the following integrals, and now we have our rules, so we can use them. So the first thing here is I have the integral of 3x plus x squared. So since that's a sum of things, I can take the antiderivatives separately. So essentially, we're going to look for the antiderivative of 3x and then the antiderivative of x squared. So antiderivative of 3x. The 3 comes along for the ride. Okay. And then essentially what I'm looking at is I'm looking at x to the first, right? Which is a power rule, if you will. Maybe I should not call it, maybe I should call it the anti-power rule. We call it the anti-power rule. So it's kind of an anti-power rule situation. So our anti-power rule says we need to add 1 to the power, so x squared, and divide by the new power. So that's kind of what I meant, Ami. That 3 is just kind of chill, and then we're just going to take into consideration just the x piece, and then the constants can be simplified and canceled out if possible later. And then we're going to add that to the antiderivative of x squared. So x squared is essentially another anti-power situation, if you will. So we're starting with 2, and we're going to add 1 to the power and divide by the new power. And again, if you like to write it as a fraction in the front, I usually do that as like a secondary step. I'm going to rewrite this in a second. And then you always tack on a plus c. So I would write this as 3/2 x squared plus 1/3 x cubed plus c. If you want to give it a function name, you can totally name it big F of x, but nah. And again, you can check your answer by taking the derivative of that, and it should get you what you started with. So you can kind of double check your work. If you take the derivative of your answer, you should get essentially the thing that you started with inside of the integral. Hooray for making sense. All right. So let's do a couple more. Feel free to stop me at any point if you have a question. because I'm kind of doing these somewhat like when we were doing the derivatives, where I'm just kind of going to keep going after I pause for a little bit. So for the next one, we have x to the fifth, and that's it. So we need to take the antiderivative of x to the fifth. So we're essentially in an anti-power rule situation. So we add 1 to the power, divide by the new power, tack a plus c at the end. You can leave it like that. I like writing it as a fraction in the front. Whatever floats your boat. Okay. For the next one, we have 12t cubed dt. So the 12 can come along for the ride. And now we need to take the antiderivative of t cubed, add 1 to the power, divide by the new power, plus c. Yeah. Catherine? Are you typing? Type in, gonna speak. If you're speaking, I can't hear you. My volume's up, right? Yeah, it is. So it's essentially because of this property right here, which tells us that if we have a constant times a function, it's equivalent to the constant times the antiderivative of the function. So just kind of like when we were doing regular derivatives, if like when we really started from scratch, I know once you get used to them, you just kind of multiply the constants together when you're doing a power rule or something like that. But when we were doing the derivatives from like very generic scratch, and we were looking at something like 3x squared and I wanted to take its derivative, the 3 came along for the ride and then we brought the power down and subtracted 1 from the power. Kind of same deal here. If there's a constant out front, it just kind of comes along for the ride. And then you take the antiderivative of the function piece. So the 12 just kind of tags along. Now, if you get good at these, like I've been doing these for so long that I know that that's going to reduce to 3t to the fourth. So if you can kind of see that there's a 4 inside of that 12 and you know how to pull it out, totally go ahead. But technically that 12 kind of comes along for the ride and then it just gets multiplied by the antiderivative of t cubed. So now we can simplify this a little bit. We can do the 12 divided by 4 and get 3t to the fourth plus c, which is what I personally would do. But that's kind of why it stays, is that that rule tells us that if we want to, we can take that constant out front and just kind of string it along for the trip. Okay. Yeah. So let's see, 7 minutes. Okay, we should get through the rest of these, which is good. Questions, concerns before I go on to the next one? Okay. Also, if you're trying to type out questions, you can almost do what she did and kind of raise your hand first and then start typing it so that I actually stop, because if you're just typing it and I don't know you're typing it, then I'm not going to stop. But if you want to raise your hand and then have me stop for a second while I'm waiting for you to type it out, you can totally do that. All right, next one though. So we have q cubed minus 6q squared dq. So we have to take each of the antiderivatives separately because it's subtraction. So the first thing we need to consider is the antiderivative of q cubed. Q cubed is kind of funny to say. So we're going to add 1 to the power, so it's going to become q to the fourth. Divide by that new power of 4. Subtract off the derivative of 6q squared, so the 6 comes along for the ride. We're going to add 1 to the power of q, so q cubed. Divide by the new power. Always put a plus c. If you want to, you can simplify it a little bit. 6 divided by 3 would give you 2q cubed. Q cubed. Now, just like with derivatives, you don't really have to simplify them if you don't want to. With these, with the constants, I always say at least simplify the constants, but if you don't, it's not the end of the world. So that's that one. I'll wait a few more seconds than usual because I gotta scroll up to get to the other one, so it'll go away. Okay. So now we've got a couple weirder ones on this right side. So we've got 8x cubed. So that's ones like we've already been treating. So we have the 8 the 8 comes along for the ride. Now we have to take the antiderivative of x cubed, add 1 to the power, divide by the new power. Now we have 1 over x. Since this is technically x to the negative first, our anti-power rule does not work on that. If you're curious as to why the anti-power rule does not work on that, if you were to use the anti-power rule there, you would add 1 to the power and divide by the new power. Dividing by 0 makes the world explode. Don't do it. So that's why you can't use the power rule on that. And that's the one that gives us the natural log of the absolute value of x. So that's why that doesn't work. So if you want to, you can simplify that to 2x to the 4th plus natural log of the absolute value of x plus c. For the next one, 12 comes along for the ride. We have an e to the kt, kx, whatever you prefer, situation here. So if you look back up at what we wrote a little while ago, the anti-power rule for e to the kx, we essentially still have e to the kx, but then we're going to have to divide by that k value. So we're going to essentially get 1 over 0.2 e to the 0.2t, always tack a plus c at the end. 12 times 1 over 0.2 is going to give you 60. So you can simplify that if you want to. Again, if you don't, it's not the end of the world. But since constants, I say go right ahead. And now we've got one more, but I'll pause in case there's a question. Okay, now here's the one that always trips everybody up. This next one does not include a natural log rule because this is equivalent to 2x to the negative 2nd plus 7. And this is actually fair game for the anti-power rule. So you need to be really careful that you don't just view anything over x to the something as a natural log thing. The only time it turns into a natural log is if it's just 1 over x. I should be careful with eventually u sub things down the line. But if it has another power on it, it's not natural log. So it would just have to be 1 over something to the first. But this is 1 over something squared, so it's an anti-power rule. So the 2 in the front comes along for the ride. Add 1 to the power, divide by the new power. Add the antiderivative of 7, which is 7x. That's kind of our antiderivative of a constant. Tack on a plus c, always and forever. Plus c, plus c, plus c, plus c, plus c. So technically, if you wanted 2x to the negative first plus 7x plus c, or if you're really fancy or just feel like it, you can put that x back in the denominator. So the only time you use the natural log one is if it's a power of 1 in the denominator. If it's more than a power of 1, it's not that. Yes, Catherine again. We're technically out of time, so if y'all have to go somewhere, feel free to leave. This is when we're done because we're out of time. But if you have questions, I'll stick around for a little bit. What's up, Catherine? You're probably typing. Keep typing. Are you talking regular derivative? I'm slightly confused by your question. So let's see if I can figure out what you're asking. Are you talking about with the constants? So remember, it's only a constant by itself that becomes 0. So like if you're talking about this 2 right here, maybe because it's next to an x term, if we took its derivative, it wouldn't go away because of the x term. The only time a derivative is 0 is if it's just a constant by itself. So something like 2 by itself, or 16 by itself. If it has an x attached to it, then it wasn't 0. Now, remember here, what we're technically doing here is we're going backwards. We're doing an antiderivative. So we're never going to have an antiderivative be 0. So antiderivatives are never 0 because that's just it. Yes, so the derivative of 2x is 2. So yes. Oh, okay. So yeah, since the 2 is attached to the x there, it does become 2. If it's 2 by itself, it becomes 0. We good now, or? No, you're fine. I'm stupid sometimes too. Sometimes I say 2 plus 3 is 6. I literally said that in my number theory class once. So, okay, cool. We good then. All right, I'm gonna stop recording. If anybody else